Wait a minute. Okay, start.
Okay. So welcome everyone to this evening session of the year-long program of Bhaskaracharya Pratisthana. So it's a great pleasure to invite Professor Kingshook Biswas from ISI Kolkata for this talk on uniformization of elliptic curves. So I invite Professor Biswas to start the lecture.
Okay. So thank you, Krishnendu, and thank you to the Bhaskaracharya Pratishthan for the invitation. So I wrote in my abstract, I'll try to keep things simple. I mean, it's aimed at students really, this talk. So I'll just try to keep things as simple as possible. So I'll be talking about uniformization of elliptic curves. And I'll explain first what I mean by uniformization. So let me start. Well, the word curves is in the title. So maybe the simplest curve that people think of often is the unit circle in the plane S1. So this is the set of points xy in R2, so that x squared plus y squared is 1. So here we have the unit circle. Now, if we want to parametrize the unit circle, we can't do it using either the x coordinate or the y coordinate, because for every x value there are 2 y values. So, and for every y value there are 2 x values on the curve. So x and y are what are called multi-valued functions of each other on the unit circle. So we can't use them to parametrize. So the question is, instead of these multi-valued functions xy, can we, so the uniformization question is, can we find a parametrization of S1 by a parameter t such that x and y become single-valued functions of t? So such a parametrization will be called a uniformization of the unit circle, because x and y then become single-valued, and or single-valued is sometimes called uniform. So they become uniform functions of t. Okay, so in that sense, instead of x and y becoming multi-valued functions of each other, they become single-valued functions of a single parameter. And of course, everyone here knows how to do that. You take the standard parametrization of the unit circle, t maps to x equal to cos t, y equal to sin t, right? So x and y become single-valued functions of a real variable t. Now, this parametrization by trigonometric functions, cos t, sin t, what I'd like to explain first is how to obtain this parametrization using complex analysis. Okay, so the first thing to do is to make the variables x and y complex. So replace x and y by complex variables z and w. So look at what we might call the complex circle, which is the set of points zw in the complex 2 space C2, such that z squared plus w squared is equal to 1. Okay, so this is a subset of C2, which is called an affine algebraic curve. That means it's the zero locus of a polynomial in 2 variables, z and w. And classically, this goes back to Riemann, that, this was Riemann's motivation for Riemann surfaces, that one can represent this algebraic curve in C2, this locus in C2, as what's called the Riemann surface of the multi-valued function w equal to the square root of 1 minus z squared. All right, so for points on this curve, w is equal to the square root of 1 minus z squared. So how can we represent this algebraic curve as a Riemann surface? So when I say Riemann surface, the modern definition is an abstract definition. It's a 2-manifold where the changes of charts are holomorphic, maps from C to C. But in Riemann's mind, a Riemann surface was a very concrete object. It was a surface given by gluing copies of the complex plane together. Okay, so what he called sheets. So it was given by gluing many sheets together. So let me explain how this arises. So let's look at this function, w equal to the square root of 1 minus z squared. So if I factor out z squared common here, then the z squared comes out of the square root. I can write this as z times the square root of 1 over z squared minus 1. All right. Now, so finding the square root boils down to finding the square root of this function, 1 over z squared minus 1. So here we can use a little complex analysis. We know that if we have a holomorphic function on a simply connected domain, which is non-zero at every point in the domain, then it has a holomorphic square root in that domain. So that's what we're going to use. So we look at this function 1 over z squared minus 1. Where is it holomorphic and non-zero? So what we do is we look at the domain, which is the Riemann sphere C hat, minus the interval from -1 to 1. All right, so this is a picture of this domain. This is the sphere. Here's the point at infinity. And you're removing the interval from -1 to 1. Now, this domain is a simply connected domain in the sphere, right? So if I look at this function g of z, which is 1 over z squared minus 1, this is holomorphic everywhere on this domain. It's holomorphic near infinity because near infinity, 1 over z squared vanishes. And so at infinity, this takes the value -1, which is non-zero. So this is holomorphic and non-zero everywhere on this simply connected domain. So therefore, complex analysis tells us that there exists a holomorphic function f on this domain D, such that g is equal to f squared on D. So we have a holomorphic square root f on this domain. Okay. So now if I look at points in my algebraic curve ZW, where z belongs to the domain D minus the point at infinity, which is the same as the complex plane minus the interval -1 to 1, then W must be either, there are two possibilities for the square root. So W is z times the square root of this function g, which is f. So W is either z times f of z or minus z times f of z. So that means if I look at the part of this algebraic curve where the z coordinate lies in C minus the interval -1 to 1, then it becomes a disjoint union of two sets, excuse me, points of the form z comma z times f of z, where z belongs to C minus -1 to 1, disjoint union points of the form z comma minus z f of z. All right. Now, both of these two sets, these are graphs over the z plane. So we can think of these, each of these, as a copy of this domain C minus the interval -1, 1. All right. So this gives us, in Riemann's mind, this would give us two sheets of a Riemann surface. So what we do is we take two copies of this domain, C minus the interval -1 to 1. So in each copy of this domain C minus the interval -1 to 1, we have a function W, which is a single valued function of z, right? We have W as the square root of 1 minus z squared, well defined here in this sheet and in this sheet. And it turns out that if you approach this interval from -1 to 1, if you approach it from the top here in the first sheet, then W converges to a limit, which is the same as if you approach this interval from the bottom in the bottom sheet. So what does that mean? That means we can glue these two sheets together in such a way by gluing the top. So you think of making a cut in this piece of paper. You open up this piece of paper. So now there are two sides, a top side and a bottom side in both the sheets. And what you do is you glue the top side of the top sheet to the bottom side of the bottom sheet, and you glue the bottom side of the top sheet to the top side of the bottom sheet. So now you have a nice two-sheeted surface. This is a Riemann surface according to Riemann. And in this Riemann surface, W is now a single valued function. of the variable. So now we have a variable z tilde on this Riemann surface. All right. And the z coordinate, so we can represent our algebraic curve as this Riemann surface. So just to get a picture for what this looks like, I've drawn two loops here. So if I start at a point in the top sheet and turn around like this, I'll come out in the bottom sheet. And if I keep turning again, I'll pass through here and come back out in the top sheet. So if I turn around twice, around -1, then I'll come back to where I started. Similarly, if I turn around twice around 1 here, I'll go from top sheet to bottom sheet and then back from bottom sheet to top sheet. I'll come back to where I started. Okay, so this is what this Riemann surface looks like. And the Z, so you can imagine there's a natural projection from this two-sheeted Riemann surface to the complex plane. And the image of a point under this projection is the Z coordinate of a point in this algebraic curve. And the W coordinate is given by these two functions, Z times f of Z and minus Z times f of Z in these two sheets. Okay. So this is how we can represent this algebraic curve as a Riemann surface, a two-sheeted Riemann surface. So this is, in modern terminology, this is what is called a branched covering of the plane. So it's like a covering map. So if I remove the points -1 and 1 from the plane, and I remove these, what are called the ramification points over here, the points which project to -1 and 1, then this becomes a genuine degree 2 covering, a connected degree 2 covering of the punctured plane C minus -1, 1. When I add in these points, at these points, this projection map is no longer a local homeomorphism. It's not locally 1-to-1. It's locally 2-to-1 near these points. So as a map between manifolds, this becomes, these points become critical points. Okay, these points become critical points. And so a branched covering is like a covering map, except you allow some critical points. Okay, where the map still has a nice local structure. All right. So so we get a two-sheeted branched covering of the plane. And now I want to consider on this Riemann surface, I consider the following function. Capital F of Z tilde is the line integral from a base point P0 up to the point Z tilde of dz over W. All right, where Z tilde is a point in this Riemann surface X, and P0 is a fixed base point in this Riemann surface. All right. So what that means is I have this two-sheeted Riemann surface, and I'll be drawing paths. So if this is P0, and say this is Z tilde, then my function is given by choosing some path from P0 to Z tilde. So my path could go like this. It goes through the top side here, comes out here, and then ends up at Z tilde here. So I integrate dz over W over this path, all right, from P0 to Z tilde. Now you may ask, what about the dependence of the integral on the path, right? So, well, we're integrating a holomorphic function here, dz over W. So Cauchy's theorem tells us that the integral will depend only on the homotopy class of the path as we let it vary with fixed endpoints. So this integral only depends on the fixed endpoint homotopy class of the path. So now we have to classify homotopy classes of paths in this Riemann surface. In other words, we need to understand its fundamental group. So we need to understand the topology of this Riemann surface. So that's not hard to do. So how is this Riemann surface constructed? We took these two sheets, we made cuts from -1 to 1, and we joined them together, right? So I can write these sheets as two spheres minus the point at infinity in each sheet. And then I'm making two cuts and joining them. So making cuts making cuts topologically, it's the same as I can open up the cut and turn it into a hemisphere. All right. So I have now two hemispheres minus a point in each hemisphere. And then I glue these two hemispheres together. That's what happens when I glue the cuts together. So what do I get? I'm gluing two hemispheres together. So we get a sphere minus 2 points, one in each hemisphere. Those are the 2 points which correspond to the 2 points at infinity in each sheet. So this is a sphere minus 2 points. So topologically, this is the same as the punctured plane, C star, C minus the origin, right? So therefore, the fundamental group of our Riemann surface, pi1 of x, is the same as the fundamental group of C star, the punctured plane, which we know is the integer z. All right. So that means that the fundamental group is cyclic, generated by a single loop C naught. So in this picture, it's a sphere minus 2 points. So the fundamental group would be generated by a curve represented by the equator, right? It goes around the equator once. So that's what I'm calling C naught. All right. And now I can understand what is the dependence of this integral on the path from P naught to the point Z tilde. So suppose I have two different paths. Let's say a path gamma 1 look like this, and a path gamma 2 which goes around the back and comes like this. Okay. So I have two paths gamma 1, gamma 2 from P naught to Z tilde. Then if I look at the path gamma 1 followed by the path gamma 2 bar, which means gamma 2 followed backwards, then I will get a loop at P naught, right? Now, since this is a sphere minus 2 points, the fundamental group is generated by C naught. Any such loop, this gamma 1 dot gamma 2 bar, this is freely homotopic to some integer multiple of the path C naught. That means the path C naught traversed n times for some integer n. So if I look at the difference of these two integrals, the integral over gamma 1 minus the integral over gamma 2, that is the same as the integral over gamma 1 dot gamma 2 bar of dz over w. And now, since these two paths are freely homotopic, by Cauchy's theorem, this is the same as the integral over C naught of dz over w. And so that will be n times the integral of dz over w over C naught. So we get this number here. That means any two paths, the integrals over any two paths, they differ by an integer multiple of a fixed constant, the integral over this equator of this dz over w. So let's call this omega naught. This is the integral over C naught of dz over w. So then that means that my integral f of z tilde, this integral from P naught to z tilde of dz over w, this is well defined modulo integer multiples of w of omega naught, right? So this takes, I can think of this integral as taking values in the quotient group C modulo the subgroup Z omega naught, the integer multiples of omega naught. So this defines for me a map F from X to C modulo Z omega naught. All right. And let's calculate what this omega naught is. So omega naught is the integral over the equator of dz over w. Now this equator I can homotop to a small loop around infinity in the top sheet. I'm calling that C. I can homotop it to a small circle. So by Cauchy's theorem, this is the same as the integral over a small circle around infinity in the top sheet. And now I can apply the residue theorem. So by the residue theorem, this is 2 pi I times the residue of this differential form dz over w at the point z equal to infinity. So how do I calculate this residue? Well, near infinity, my local coordinate is 1 over z. So I take the variable t equal to 1 over z, and I write this differential form dz over w in terms of 1 over z. So dz over w is dz divided by w, and w was z times the square root of 1 over z squared minus 1. So since t is 1 over z, this dz over z is the same as minus dt over t. And this 1 over z squared minus 1 becomes t squared minus 1 to the half. So now you use the power series expansion for 1 over t squared minus 1 to the half. And you have this 1 over t outside, minus 1 over t. So what you'll get is, you'll get dt times a Laurent series, which starts with plus minus I over t. And then you have holomorphic terms, constant and then positive powers of t. So that means the residue is plus or minus I. So what will happen is the residue at the first point at infinity will be plus I or minus I, and the residue at the other point at infinity will be the negative of the residue at the top point at infinity. Okay, so the residues at these 2 points at infinity will be negatives of each other, plus or minus I. So now let's suppose the residue is minus I. So then omega naught becomes 2 pi I times this residue minus I. So that becomes 2 pi. So this integral over the equator of dz over w, this is nothing but 2 pi. So that means my map F, it takes values in x. I mean, it maps my algebraic curve x to the quotient C modulo 2 pi z. So this you can think of as a complex cylinder, right? If it was R modulo 2 pi z, you get a circle. If it's C modulo 2 pi z, you get a circle cross R, which is a cylinder. And what one can show is that this map F is 1-to-1 and onto. And so, in fact, we can look at its inverse, and let me call G equal to F inverse. So I'm not going to show that it's 1-to-1 and onto. So that goes in the opposite direction from this complex cylinder, C modulo 2 pi z, back to the algebraic curve. Now I take P to be the quotient map from C to the complex cylinder, C modulo 2 pi z. And then I compose it with this map G, which is the inverse of this integral F from C modulo 2 pi z to x. So I look at this composition, G composed with P, I call that phi. So that goes from C to C modulo 2 pi z to x. So notice that since it factors through the quotient map, phi of t plus 2 pi is equal to phi of t, because the quotient map sends t and t plus 2 pi to the same point here in the quotient. So now, if I look at my function zw on the algebraic curve, so those are maps from x to c, then if I look at z composed with this map phi and w composed with this map phi, those give me functions from c to c. And since phi is 2 pi periodic, that means that these functions will be 2 pi periodic functions of t. So, so this z becomes phi of t, a 2 pi periodic function of t. And you can see now that it's going to be minus cos t. And this z composed phi t rather becomes minus cos t. And w composed with phi t becomes sin t. And so the pair zw is equal to minus cos t comma sin t. So why is this true? Because t, remember, the variable in the plane is given by integrating dz over w. So that's the integral of dz over square root 1 minus z squared. W was square root 1 minus z squared. So this integral everyone knows, this is minus cos inverse z. So that means t is minus cos inverse z. So z is minus cos t, or, oh, there's a mistake here. Z will be just cos t. Yeah. Sorry. There's a minus t and then you take cos. So z will be cos t. And then from this t equal to integral dz over w, we have dt is equal to dz over w. So if I solve for w here, that means w is dz over dt. So if z is cos t, then w will be minus sin t. Okay, so what I get is cos t and minus sin t. So w will be minus sin t and z will be cos t. So in other words, I've got the parametrization that I wanted. Z and w become functions of t, cos t and minus sin t, right? They become 2 pi periodic functions of t, of a complex variable t. And this map phi, which was, I remind you, you go from C to the cylinder C modulo 2 pi z, and then you go by the inverse of what's called this abelian integral. So this integral here, integral dz over square root 1 minus z squared, this is an example of what's called an abelian integral. So it's the integral of a rational function, an algebraic function of z. So classically, these are called abelian integrals. So what we did is we inverted the abelian integral, and then we composed with the quotient map from C to C modulo 2 pi z. And so we get a map from C to X, which is 2 pi periodic. And this map is in fact is a holomorphic map, which is the universal covering of X. So this map is called the uniformization of X. Okay. So in this way, we found our uniformization of the circle by passing to complex coordinates, considering an abelian integral, and then inverting that abelian integral. The inverse of the abelian integral is a singly periodic function, which gives us our parametrization. Now the same method works to uniformize any algebraic curve of the form w squared equal to a quadratic polynomial in z. Z minus Z1 into Z minus Z2 with distinct roots. So Z1 is not equal to Z2. Again, you'll consider the integral dz over W, and you can perform the same steps and uniformize this algebraic curve. So you will get a parametrization of this also by singly periodic functions. So they will be trigonometric functions. So these algebraic curves can be uniformized by trigonometric functions. So now we come to elliptic curves. So instead of looking at an algebraic curve w squared equal to a quadratic in z, a quadratic polynomial in z, an elliptic curve is given by looking at the algebraic curve w squared equal to a cubic polynomial in z, so with roots z1, z2, and z3, which I assume are all distinct. So now we can do the same thing that we did for in the previous example. We look at the Riemann surface of this multivalued function, w equal to the square root of this cubic polynomial. So here, what happens is, if we want to find a single valued branch of this square root, we can do so in the following domain. So this domain is going to be a bit different now. So we have these 3 points, Z1, Z2, and Z3. What I do is we join Z1 to Z2 by a simple arc, and we join Z3 to infinity by a simple arc. So this domain I can write as an intersection of two domains, V intersection W, where V is equal to the plane minus the arc from Z1 to Z2, and W is equal to the plane minus the arc from Z3 to infinity. And now, so we have D is this V intersection W. Now I look at each of these domains individually. So my multivalued function W, I can write as the square root of Z as Z into the square root of 1 minus Z1 over Z, 1 minus Z2 over Z, into square root Z minus Z3. So I have to find square roots of these two functions, 1 minus Z1 over Z into 1 minus Z2 over Z, and the function Z minus Z3. So this first function, let me call it G of Z. This is 1 minus Z1 over Z into 1 minus Z2 over Z. So this is again holomorphic and nowhere zero on the domain V union infinity, which is a simply connected domain. This domain is not simply connected, but if I add the point at infinity, then it becomes simply connected. So G will be therefore equal to some holomorphic non-zero function f1 squared on this domain V. And my second function H is Z minus Z3. This is holomorphic nowhere zero on this domain W, which is simply connected. So H is equal to some function f2 squared on W. So both of these have square roots on V and W. So therefore on the intersection, V intersection W, I can write my multivalued function little w as Z times the square root of G times the square root of H. That becomes either Z times F1Z into F2Z or minus Z into F1Z, F2Z. Okay. So now I get, like I did in the previous example, a two-sheeted Riemann surface where what I have is two sheets where I make cuts from Z1 to Z2 and from Z3 to infinity in each sheet. And then I glue the two sheets along the top and bottom sides of the cuts. Okay. So it's similar to what we did earlier. So topologically, what do we get now? So here we have a sphere minus two cuts from Z1 to Z2, Z3 to infinity. So if I open up the cuts, what will I get? I'll get a finite cylinder, right? I enlarge these two cuts into holes. So topologically, we get a finite cylinder here. And what we're doing is we're gluing these two half cylinders. And so what do we get? We get a torus. So now my Riemann surface, this algebraic curve, this is now a torus, except we don't have the point at infinity. So this is a torus minus a puncture, minus a point at infinity. So if I want a nice compact Riemann surface, then I define x hat to be x union infinity. So I add in a point for the puncture, and this gives me a compact Riemann surface of genus 1. So this is homeomorphic to a torus. All right. And now on this, so this elliptic curve is a torus after I add in a point at infinity. Now on this elliptic curve, I want to consider the same abelian integral. So I look at f of z tilde is the integral dz over w. Okay. So now I look at this one form dz over w. This is a holomorphic one form, which is non-zero on x hat, this compact Riemann surface, this torus, minus these 4 points. So outside these 4 points, z1, z2, z3, and infinity, this one form is holomorphic and non-zero. Okay. So what I want to say is that this extends to a holomorphic one form on the whole compact Riemann surface. So I need to check that this dz over w is a holomorphic one form at the points z1, z2, z3, and infinity. So to do that, I need to find local coordinates near these points. So my algebraic curve x is of the form some polynomial p of zw equal to 0, where p of zw is w squared minus a polynomial q of z. Q is this cubic polynomial. So how do I find local coordinates? So for that, I can use the holomorphic implicit function theorem. So if I take a point z0, w0 in this algebraic curve x, then if del p del w at z0, w0 is non-zero, so then by the holomorphic implicit function theorem, we can write w as a holomorphic function phi of z for zw in the algebraic curve close to z0, w0. Right? By the implicit function theorem, we can solve for w as a holomorphic function of z near z0, w0. What that means is if I look at the projection map, z comma w maps to the first coordinate z, then this has an inverse, z maps to z comma phi of z, because w is equal to phi of z. So these two are continuous maps which are inverses of each other. So therefore they are homeomorphisms in a neighborhood of z0, w0. So that means that the z coordinate, this is a local coordinate for this Riemann surface near the point z0, w0, if del p del w is non-zero. Okay, so near a point of the algebraic curve, if del p del w is non-zero, then z is a local coordinate. And similarly, if del p del z is non-zero, then w will be a local coordinate for the algebraic curve. So now let me look at the points on the curve where the z coordinate is equal to one of the roots of the polynomial, the cubic polynomial q. Okay, so what are these points on the algebraic curve? So here z is equal to zi, I goes from 1 to 3, and w is equal to 0, because w squared is q of zi, which is 0, so w is 0. So I have these 3 points on the algebraic curve, zi comma 0. So I compute the partial derivatives, del p del w at zi comma 0. So p was w squared minus q of z. So del p del w is just 2w. So that is 0. But del p del z will be minus q prime z. And so that's minus q prime zi. And this is non-zero because q has distinct roots. So the roots are simple. So Q prime is non-zero at the zeros. So that means that since del P del Z is non-zero, that means that W is a local coordinate near these points of the algebraic curve, Zi comma 0. So now I look at the equation W squared equal to Q of Z. So if I differentiate, I take derivatives on both sides. This tells me that 2W dW is equal to Q prime Z dZ. So I can solve for dz over W. This becomes equal to 2 divided by Q prime Z dW. Okay, and now W is a local coordinate, and 2 over Q prime Z is holomorphic and non-zero near this point Zi comma 0, because Q prime of Zi is non-zero. So that means that dz over W is a non-zero holomorphic function times dW near these points of the algebraic curve, where W is a local coordinate at these points. So therefore, this differential form is holomorphic and non-zero at these 3 points on the algebraic curve. Okay. So what remains is now the point at infinity on the algebraic curve, on this Riemann surface x hat, which is a torus. So I need to find a local coordinate near the point at infinity. So we look at the part of the algebraic curve where the z coordinate is bigger than some large number r, where mod z is bigger than r. So that will look like the part of the sheets outside a ball of radius r. So it will look like the complement of 2 disks glued together. So here I have a well-defined square root function. All right, the square root of z tilde is single valued here, and that will, the square root will map this 2 shaded region to the complement of a disk of radius square root r. All right, and now I've mapped it 1-to-1 onto the complement of a disk, and now I can look at, so this is my map xi equal to square root of z tilde, and then I take a new variable t equal to 1 over xi. So then that will map the complement of this disk inside a disk minus a point. And so if I add in the point at infinity, that will map to the origin. So this will give me a 1-to-1 onto map onto a disk. So that means this t coordinate here, this is my local coordinate near the point at infinity. All right. So t is equal to 1 over xi, which is 1 over square root z tilde. This is my local coordinate near infinity. So what is z? Z is xi squared. Xi was the square root of z. So z is xi squared, which is 1 over t squared. So what is w? It is the square root of q of z. So I write that as z times square root z times the square root of this function. Now this function inside the square root is holomorphic and non-zero near infinity, when z is near infinity. So I can write this as some holomorphic non-zero function f of t. And I have now z into square root z. So z is 1 over t squared. So z into square root z will be 1 over t cubed. So that means w in terms of the local coordinate t is 1 over t cubed into f of t. Okay. So now what is dz over w? Well, z is equal to 1 over t squared. So if I differentiate here, then dz will be minus 2 over t cubed dt, and w will be 1 over t cubed f of t. So the t cubed and the t cubed cancel. So this what remains is just minus 2 over f of t dt, where f is non-zero and holomorphic. And when t is near 0. So that means this differential form therefore is holomorphic, because it's a holomorphic function times dt, where t is a local coordinate. And it's also non-zero. It's also non-zero, since f is non-zero near t equal to 0. So what do we get? In summary, we've shown that our differential form dz over w, which was holomorphic and non-zero outside these 4 points on the algebraic curve, z1, z2, z3, and infinity, it extends to a holomorphic one form on the whole torus, which is non-zero everywhere on this whole torus. That means I can integrate over all paths in this torus. Okay. So now I need to calculate, when I do the abelian integral, what is the ambiguity in the integral. So again, I need to find the fundamental group. So the fundamental group of this torus, we know, is generated by these two circles, A and B. So if gamma is a closed curve in this torus x hat, then gamma is freely homotopic to an integer multiple of A plus an integer multiple of B for some integers m and n. That means the integral over any loop of dz over w is an integer m times the integral of dz over w over the A curve plus an integer n times the integral of dz over w over the B curve. Okay, so these two numbers here, integral of dz over w over the A curve and over the B curve, these generate, so we're looking at the subgroup of C generated by these two complex numbers. So that is, I'll call that group L. So this is Z omega 1 plus Z omega 2. This is the subgroup of C where omega 1, omega 2 are these two integrals. Okay. And as before, the multivaluedness in this abelian integral, it's given by the integral over loops. And the integral over loops belongs to this subgroup L. So that means my integral, I can think of it as taking values in the quotient C modulo L. Right? So this abelian integral now takes values in this quotient C modulo L. Now, what does C modulo L look like? Well, it's a fact which I won't prove. One can show that these two integrals, omega 1 and omega 2, over the A curve and the B curve, these are actually linearly independent. Okay, so this follows from a classical relation of Riemann's called Riemann's bilinear relations. So, so you can show that omega 1 and omega 2 are linearly independent over R. So if I look in R, then here's omega 1, here's omega 2. The subgroup generated by omega 1 and omega 2 will therefore be what's called a lattice in C. So that's a free abelian group of rank 2 with generators omega 1 and omega 2, such that it's a discrete subgroup of C, and the quotient is compact. So what is the quotient? So here, under the action of this subgroup L, I can move any point in C into this fundamental parallelogram. So this is what's called the fundamental domain for this group L acting on C by translations. And so the quotient of C by this group L, this subgroup L, will be the same as quotienting this fundamental parallelogram by these two translations. So when I identify the sides of these opposite sides of the parallelogram, I get again a torus. So this quotient C modulo L is a torus. And now what do I have? This map F, this abelian integral, it goes from x hat, this which is a torus. X hat is this algebraic curve with a point at infinity. This is a torus, and it maps to a complex torus, C modulo L. So this becomes a holomorphic map between tori. Both of these are Riemann surfaces. This becomes a holomorphic map between two tori. So what we're going to show is that this map is actually a biholomorphic map. So it's a holomorphic diffeomorphism between these two Riemann surfaces. So it can be inverted. So how do we show that? So first, F is given by this integral, P0 to Z tilde dz over W. So that means that df is equal to dz over W. Now we showed that this holomorphic one form dz over W, this is nowhere zero on x hat. So since this is nowhere vanishing, that means df is nowhere zero. So therefore, by the inverse function theorem, f is a local diffeomorphism everywhere, because its derivative df is nowhere zero, because this differential form is nowhere zero, dz over W. And now it's a local diffeomorphism between two compact manifolds without boundary. Both are tori. And so therefore, it must be a covering map. Right? This is a standard fact. If you have a local diffeomorphism between compact manifolds without boundary, then it is a covering map. So F is now a covering map. So we want to show that this covering map is actually a homeomorphism, is one-to-one. Then it will be a diffeomorphism. So we look at the induced action on the fundamental group. So from pi1 x hat So that's generated by the A curve and the B curve, to pi1 of this torus C modulo L. So pi1 of C modulo L, I can identify with the lattice L. So it's Z omega 1 plus Z omega 2. And because omega 1 is the integral of this differential form over the A curve, and omega 2 is the integral of dz over W over the B curve, it's easy to see that the induced map F star between fundamental groups, what will it do to the A curve? That will correspond to integrating over the A curve this differential form. So that will map to omega 1 in the fundamental group of this torus C modulo L. So that means that the A curve will map to omega 1 and the B curve will map to omega 2. So in other words, this maps the generators of this free abelian group A and B to the generators of this free abelian group omega 1 and omega 2. So therefore, this map between fundamental groups is an isomorphism, right? It maps generators of the free abelian group to generators of the free abelian group of rank 2. So this is an isomorphism. So since my map is a covering map and the induced map on fundamental groups is a isomorphism, that means that my map actually is a homeomorphism, right? So now I have a homeomorphism. So F is a holomorphic diffeomorphism. So now I can do the same thing that I did in the first example, which is we invert this abelian integral. So I know it's a diffeomorphism, it's 1-to-1, so we have an inverse. So I let G be the inverse, F inverse. So now this goes from the torus C modulo L to the algebraic curve X hat. And I let P be the quotient map from C to C modulo L. Now I do the same thing that I did before. I look at phi, which is the composition of G with P. So this goes from C to C modulo L, and then from C modulo L to the algebraic curve X hat. So because phi factors through the quotient map, phi is going to be a doubly periodic map. So that means phi of T plus omega 1 and phi of T plus omega 2 will both be equal to phi of T, because this is true for the quotient map. So now if I look at Z composed with phi and W composed with phi, then that means, so these will map from where to where? These will map from C to C hat, because Z and W map the algebraic curve X hat to C hat. So the composition will go from all the way from C to C hat. So what kind of functions will these be? These will now be doubly periodic meromorphic functions. So to summarize, when we inverted the algebraic curve W squared plus Z squared equal to 1, we inverted the abelian integral corresponding to that algebraic curve. There we got singly periodic functions, which were trigonometric functions. Now, if we invert the abelian integral corresponding to the elliptic curve, y squared equal to a cubic in x, then we get doubly periodic meromorphic functions, and these are called elliptic functions. So these are not expressible in terms of trigonometric or exponential functions, because those are singly periodic. These are doubly periodic. These have two periods which are linearly independent, omega 1 and omega 2. So finally, we get a parametrization of the algebraic curve by doubly periodic functions. So let's call P of T to be the Z coordinate composed with this map phi of T, and Q of T is the W coordinate composed with phi of T. So we have that as before, dt is dz over W. So if I solve for W, then W, which is Q of T, is the same as dz over dt. So Z was P of T. So this will become dp dt. So that means Q of T is dp dt. So Q is equal to P prime. So just like we had cos and minus sine for the complex circle, W squared plus Z squared equal to 1, here we get a parametrization T maps to PT comma P prime T. Okay, so this is a parametrization of the elliptic curve by doubly periodic functions. Right, so this is the uniformization of the elliptic curve that we were looking for. And it comes by inverting an abelian integral. Just the same way that trigonometric functions, cos t, sin t, come by inverting an abelian integral. Okay. And to finish, I'll just say what this function P is. You can give an explicit formula for this. This is a well-known elliptic function. That means a doubly periodic meromorphic function called the Weierstrass P function. So if we write our elliptic curve in the form w squared equal to 4 times this cubic, then in fact this function P of t is given by an infinite sum. It's 1 over t squared plus a sum over omega in the lattice non-zero, 1 over t minus omega whole squared minus 1 over omega squared. So because we're summing over the lattice here, it's possible to show that this function is doubly periodic. So it's invariant under translations from the lattice L. And this is what's called the Weierstrass P function of the lattice. Okay, so our uniformization of the elliptic curve is given by, similar to the uniformization of the unit circle, cos t minus sin t. Here it's given by P comma P prime, all right, where P is the Weierstrass P function. So I'll stop here. Thank you. Okay.
So in one of our talks, these elliptic functions are related with the modular group.
Correct. Yes.
So how to bring that picture of modular group in your discussion?
I see. I can explain that a bit. So where the modular group comes is when you vary the parameters of the elliptic curve. So a general elliptic curve. So if I vary Z1, Z2, and Z3, the coefficients of the elliptic curve. So my elliptic curve will be, let's say, y squared equal to 4x cubed minus g2x minus a constant g3. I can bring it into this form. And if I remember correctly, where G2 and G3 will be functions of the lattice. So this will be G2 of L. So you see, as soon as I have an elliptic curve, I get a lattice. The lattice is generated by these two periods, omega 1 and omega 2, where omega 1 and omega 2 are these two abelian integrals. The integral of dz over w over the A curve and over the B curve. Right? So these two are linearly independent. They generate a lattice for me. So any elliptic curve gives rise to a lattice. So the coefficients I can think of as functions of the lattice. Because this what you can show, this is y is p prime and x is p. So this is 4 p prime is 4p cubed minus g2p minus g3. And so these G2 and G3, you can solve for these. These turn out to be sums over the lattice. So these are sums. If I remember correctly, this is the sum 1 over omega to the 4 over the non-zero elements of the lattice, L modulo 0, L minus 0. And G3 is the sum 1 over omega to the 6. Okay, sum over the lattice. So now notice that these are sums over the lattice. These are homogeneous functions of the lattice. So if I look at lattices in C, then if I look at the set of lattices L, so let me look at script L is equal to the set of lattices L in C. So I can multiply any lattice by a non-zero complex number to get a new lattice. So C star acts on this set of lattices. Okay. And so what is the quotient L modulo C star? So it turns out that I can, if I have any lattice with generators omega 1 and omega 2, then I can just divide by omega 1. So I multiply by 1 over omega 1. So then the generators become 1 and some number tau in the upper half plane. Okay, so I get new generators 1 and tau of the lattice. And now this lattice is, here I chose 2 generators and I divided by the first generator to get the tau. So there is an ambiguity in tau. If I choose a different set of generators, then they will be of the form A omega 1 plus B omega 2 and C omega 1 plus D omega 2, where the matrix ABCD is in SL2Z. So now maybe you're starting to see where the modular group will come in. So this tau is equal to omega 2 over omega 1 or omega 1 over omega 2. If I divide by omega 2, let's say, no, I think it's omega 2 over omega 1. That should be fine. So if I change this, then I get a tau prime. If I change my basis of the lattice, I get a tau prime. So this is my new basis of the lattice, omega 1 prime and omega 2 prime. So this will be omega 2 prime divided by omega 1 prime. So this will be C omega 1 plus D omega 2 divided by A omega 1 plus B omega 2. So if I divide both by omega 1, then what happens is that tau prime is equal to C plus D tau over A plus B tau. In other words, it's equal to an element of PSL2Z, the Mobius group, the modular group acting on tau, right? So this is equal to some gamma of tau, where gamma belongs to PSL2Z. So in other words, what it means is that this space of lattices modulo C star, this is isomorphic to, this can be identified with the upper half plane modulo the modular group, PSL2Z. Okay, acting by Mobius transformations. And what happens is these homogeneous functions of the lattice, these correspond to modular forms, which are differential forms on this Riemann surface. These are holomorphic differential forms on this Riemann surface. So that's how modular forms enter the picture. When you consider varying the space, variations in the space of elliptic curves, the coefficients of the elliptic curve, which are functions of the lattice, they are homogeneous functions of the lattice. Those correspond to, so G2, G3 actually correspond to modular forms. So these are modular
G2,
forms.
G3 are kind of like Eisenstein series.
Correct. Similar to Eisenstein series. Yes. I mean, you can write these in terms of Eisenstein series, these G2 and G3. The Eisenstein series, I think, generate.
I mean, that summation over the lattices, those two summations.
Right. So
these
are modular forms. So this is how these modular forms enter the picture. you look at lattice's modulo complex multiplication, that is identified with the modular surface, H modulo PSL2Z. And homogeneous functions of the lattice correspond to modular forms. They correspond to modular forms in this picture. So that's how modular forms enter the picture. Yeah.
Okay, good. Thanks.
So if phi is a subgroup of PSL2Z of finite index.
Sorry?
If I take a subgroup of finite index in the modular group,
Yes, yes.
then that H mod phi is some parametrized family of elliptic curve with some structure.
Correct. That's right. This is the family of all elliptic curves, but if you take a finite index subgroup of PSL2Z, then you get family of elliptic curves with some restrictions, with some extra structure.
With some extra structure on that.
With some extra structure. For example, the torsion points.
Yeah.
Torsion points on the elliptic curve. So, yeah, that's right. Yeah, that's
right. Yeah. So I have just one question. So
yes.
Here, you know, when you take the space of all elliptic curves,
right.
Okay, you take any 2 points. I mean, both of them topologically represent the same torus.
Right. See, it's basically it's like the Teichmuller space.
Yeah,
so,
no, but my question, So their fundamental groups are isomorphic to SL2Z, but I mean, they are non-conjugate, you can say, right? I mean, they are non-conjugate.
The fundamental groups are both Z2. They're tori.
Z2, sorry, Z2.
Right.
Yeah, Z2, but they are non-conjugate subgroups of PSL2Z.
No.
Or PSL2R.
No. They're non-conjugate subgroups of C. They're two lattices.
Oh, they are non-conjugate subgroups of C, I see.
Because it's a quotient of C. The universal cover is C here.
C here, right.
Not the disk. It's not the disk. It's the upper half plane. Right, they're tori. The tori are quotients of C modulo lattice.
C modulo lattice.
That's what we find by inverting this abelian integral. We get an explicit map from C modulo some lattice to the tori. Right?
Yeah, and SL2Z is the automorphism group of that tori.
No,
right.
SL2Z is the mapping class group of the torus. It's
the mapping class group of the torus.
It's the mapping class group of the torus.
Yeah. So now, if you take any 2 point on this L mod C star,
yes,
or in your space of lattices, so their mapping class groups will be isomorphic, or they will be. What is the relation between these mapping class groups?
No. See, the mapping class group is a purely topological object. So
right.
What you're doing is you imagine just a topological torus, all right?
Yeah.
And then on that topological torus, you're looking at all possible complex structures on that same torus.
Yes.
So different charts, different atlases, right? On the same complex,
same
topological torus. And,
right.
What happens is, I mean, this upper half plane is what's called the Teichmuller space of the torus. So that means you have to introduce a notion.
Oh, I see. So the map.
The mapping class is, the mapping class group, it acts on the Teichmuller space. It acts on the Teichmuller space, which is the upper half plane. And the quotient is what's called the moduli space. So the moduli space is all complex tori up to biholomorphism.
Okay.
It's complex tori up to biholomorphism. So, right. So the PSL2Z, you can think of it as the mapping class group of the torus acting on the Teichmuller space, which is the upper half plane.
Right.
That's the way to think of it.
Yeah. And this Teichmuller space, I mean, they are parametrized by this tau, whatever you have defined, this this number, right? So
right.
Okay.
In this isomorphism, lattice by C star equal to H by PSL2Z.
Yes.
So in PSL2Z, we know certain special elements.
Right.
Like elliptic point.
Yes. Oh, so for example, the special points in in the upper half plane, you have, so this is the usual picture of the fundamental domain. So you have these torsion points. Sorry, here it is. This is the, right. So there, here's I, and this is, I think, omega, right? And
Omega square.
is this omega? No, this will be omega, right? This is the
Other one is omega square, right?
No, omega squared will be somewhere here.
Okay.
Right? I mean, this angle is pi by 3, 2 pi by 3. I mean, 120 degrees, 120 degrees. So I think this will be minus omega. So anyway, these 2 points in the quotient, they're identified because, I mean, this is just omega minus 1. This is just omega minus 1. So these 2 are identified. So in the quotient, they're the same. They correspond to the lattice, the triangular lattice, where which is generated by 1 and 1 and omega. So you can also think of it as generated by 1 and omega plus 1. Oh, sorry, minus 1, omega minus 1. Yeah. No, sorry, plus 1. It will be plus 1. Yeah, that's right. So this is the lattice with, so this has an extra symmetry. And then I corresponds to just the square lattice. I corresponds to the square lattice. So this also has a symmetry of order 4. And this has a symmetry of order 3, this lattice. So, I mean, those correspond to stabilizers. In the modular group, this has a stabilizer of order 2, and this has a stabilizer of order 3 in the modular group. Is that what you are asking? I'm sorry, maybe.
Yeah, same. And there would be an extra point like cusp.
Right. Right. The cusp occurs when basically the lattice becomes the torus sort of it degenerates. It becomes very thin. So the torus becomes very thin.
Okay.
I mean, basically you're looking at a lattice 1 and tau going up. So this is your lattice, right? So it's looking very thin. Here's 1 and here's tau. Tau is going up to infinity. So you're getting a very thin torus. So the torus is degenerating as you go to infinity. The torus will be the quotient of this rectangle. So it will be a thin torus.
Yeah, thanks.
Okay, so any more questions, comments? Okay, if not, then let's thank Kingshook for this wonderful lecture. I mean, it was a very nice talk, especially for the students. Yeah, so thank you, Kingshook.
Sure. Thank you for the invitation.
Yeah, I see you in a week or so at ISI Mohali.
Please remind me. I don't remember.
Yeah, I will remind you. I mean, we will remind you. Yeah.
Yeah. All right. Okay. Thank you then.
Bye.
I'll stop sharing. Bye.
Ganesh, you can stop things.